In this lesson, we're going to learn some properties that will help us to simplify expressions that have logarithms. Now, if we keep in mind that logarithms are in fact exponents, then it should be reasonable to think that the properties of logarithms will be similar to those properties of exponents that we learned in beginning algebra. So let's start off with a few basic properties, recognizing that in these properties, all the values of b that you see are going to be expected to be positive numbers, because in these expressions, the b will be the base. Any other variable, any other n value that you see will always be any real number we want. So let's start off with this property. This is saying that no matter what the base of a logarithm is, if the argument is ever 1, then the answer will automatically be 0. Now, it should seem reasonable if you just convert this into exponential form, because b to the power of 0 will equal 1. So if you look at any property or any example here showing that the argument is 1, regardless of the base, log base 3 of 1 will be 0. In this next example, we could see that if the base and the argument are the same number, then the answer to that logarithm will always be 1. Now again, if we think of it in terms of exponential form, that would imply that a base of 0 raised to the power of 1 is what's going to give me the base inside of the argument. So if you look at log base 5 of 5, or log base 10 of 10, or log base 2 of 2, those are always equal to 1. Now this next property is relatively helpful to simplify logarithms that have arguments that are not necessarily equal to the base, but an argument that can be simplified to be that base to some power. So notice that if you have log base b of b to any power, the answer is that power. So it looks very similar to property 2, except property 3 now has an exponent inside of the argument. Now this should be reasonable as well, because b to the power of the exponent of n on the right side is obviously what equals the argument of b to the power of n. So let's look at an example here. If we have log of 10 cubed, remember that 10, or a logarithm without a base drawn or a base written, is always going to have a base of 10. So log of 10 cubed means the same thing as log base 10 of 10 cubed. And because the argument has the same base as the base of the logarithm, the answer is 3. Now this is the inverse property of number 4. This is saying if the logarithm has a base of b, as does the exponent, this one down here is saying if the base is b raised to a power that's a logarithm. Either way we look at this, the output is going to be n. Let's see why this works, because if I were to convert this into a logarithm, if we convert this into a logarithm, now we can recognize that since the base of this exponential is b, we can rewrite this as log base b of the other side, which is n, is equal to the exponent of log base b of n. Which is why it should make sense that if we have 4 to the power of a logarithm that also has a base of 4, the answer is nothing more than the argument, which is 15. Now these are a few basic properties that allow us to simplify logarithms that involve only numbers. So we can see that all of the arguments here are numbers, and these properties allow us to come up with the result. But these aren't the only properties. There are 3 more properties that are going to allow us to simplify other forms of logarithms. And this first one is going to relate to the property that says b to the power of x times b to the power of y is equal to b to the power of their sum. So we know that this is a property of exponents that allows us to say when I'm multiplying 2 exponentials with the same base, I can add the exponents. Well, it turns out that there's a product rule for logarithms as well. So the property that we're going to look at is going to be very similar to the property of exponentials. But what this is telling us is that if the argument is ever a product of 2 different factors, that I could separate this into two separate logarithms by addition. So if the product inside of a logarithm is m times n, then I could break this up into two logarithms, one that has the argument of m, one that has the argument of n, but we add the two logarithms together. Now this is the property, but I'm going to go through the proof just to demonstrate why this makes sense. So keep in mind that logarithms are exponents. So why don't we think about the value of x being a certain logarithm and the value of y being a certain logarithm, because exponents are logarithms. So let's set x equal to log base b of m, and let's set y equal to log base b of n. Now, if we look at the argument of m times n, then we could recognize that m times n could be written in a certain form if we only changed this into exponential form. So if x is log base b of m, then that means that b to the power of x is the value of m. And if log base b of n is equal to y, then by changing to exponential, we know b to the power of y is equal to n. So we can now do a substitution to see that m times n is actually b to the power of x times b to the power of y. But by the property of exponentials, we know that we can simply add the two exponents together. So now we know that m times n is the same thing as b to the power of x plus y. So let's now convert this new logarithm, or I'm sorry, this new exponential back into a logarithm. Notice that the base is b, so we could rewrite this as log base b of m times n is the exponent of x plus y. But going back to what our setup was, x is log base b of m, and y is log base b of n. So we can now just substitute for x and y, and we get our property that's stated right up above. So this product property is going to allow us to convert from a single logarithm that has a product inside to a multiple logarithms that are being added, or we could combine multiple logarithms of the same base by merging them together into a single logarithm. Let's look at a couple examples. So here we have a single logarithm, and we're expected to expand it. Now notice that this argument is 8 times x times y. So we can actually rewrite this using the product property. Now because this is a product between 8 and x times y, then we can break this apart into log base 2 of the first factor plus log base 2 of the second factor. Now notice that x times y is another product, so we're going to be able to separate those as well. And we should recognize that log base 2 of 8 can be written as log base 2 of 2 to the third. The reason we would do this is because 8 is a particular exponential form, has 2 to the third. And now we can see that log base 2 of 2 to the third will simply become the exponent of 3. As we take a look at log base 2 of x times y, we can break those apart through addition as well, which means my final result is 3 plus log base 2 of x plus log base 2 of y. Now we know that we've finished if we don't see any more products inside of a logarithm. Let's take a look at another example here that's actually supposed to be condensed now. Notice how this one says to expand because it's a single logarithm, while this one has multiple terms, multiple logarithms that we want to condense into a single logarithm. So let's start off by combining ln of a plus ln of b, which becomes simply ln of a times b. But notice that we can rewrite 2 as a logarithm as well. We'd like to think, how can we write 2 as a natural log of some number? Well, by that property that says that if the bases of the argument and the logarithm are equal, then the answer is simply the exponent. That must mean if we know the base of the natural log is e, we could write the argument as e to the power of 2, which should simplify to 2. But now that it's a logarithm being added to another logarithm, I can combine them by the product property to get the natural log of e squared, times AB. So this demonstrates how we can apply the product property in order to expand and condense logarithms. But this isn't the only property. We could use another property of logarithms that's related to this property of exponents that says that if you're ever just dividing two quantities with the same base, that you could simply subtract the exponents, which would imply for a logarithm that we're allowed to do something very similar since logarithms are exponents. So it looks like if you're ever taking a logarithm of a quotient, that I could separate this by subtracting the two separate logarithms. Now again, keep in mind, logarithms are exponents. So if we think of x and y as being two separate exponents, then whenever I'm dealing with a quotient of two exponents, I can subtract the exponents, which is why I can subtract log base b of m minus log base b of n if I ever see a quotient inside of a logarithm. So let's take a look at a proof before we look at an example. Let's do something real similar to the proof we did last time, where we let the x and y values be different logarithms. X and y are exponents. So let's rewrite x as log base b of m, and let's rewrite y as log base b of n. Now converting these into exponential form gives these two forms, b to the power of x is equal to m, and b to the power of y is equal to n. So now you realize that in the original exponential property, we have b to the x divided by b to the y. So why don't we realize that b to the x and b to the y are simply m and n. So we could write that as m over n is equal to b to the x over b to the y. But notice that that allows us to now just subtract the exponents, which is how we get that m over n is equal to b to the power of x minus y. This is now a single exponential equation if we disregard the middle equation here. And therefore we could rewrite this as a logarithm. We could say log with the base of b of m over n is equal to the exponent of x minus y. Again, just converting from an exponential form into logarithmic form. But by doing a substitution from the beginning of this proof, x is simply log base b of m, which can be replaced with our x, and y is log base b of n, which can be replaced with y. And therefore my final property is log base b of m over n is equal to log base b of m minus log base b of n. In other words, if you're ever dividing inside of an argument, we can separate it into two separate logarithms through subtraction. So let's take a look at a couple examples now. Now I realize that I'm expanding a single logarithm into multiple logarithms. First thing I should do is recognize that square root of 7 over xy is the argument of this logarithm. So I could break this apart by simply subtracting the two logarithms with the numerator and the denominator. Now I'm going to take a look at log base 7 of the square root of 7. Remember that we like when the base of the logarithm is the same as the base of the argument. But notice that that square root is messing some things up. So why don't we rewrite the square root of 7 as 7 to the power of 1/2. And now over here, log base 7 of x times y, notice that's a product rule. Since I've got a product inside of an argument, I can split that apart through addition. So I could rewrite log base 7 of xy as log base 7 of the first plus log base 7 of the second. But there's one very important part of this that's missing here. Notice that we're supposed to be subtracting the entire log base 7 of xy, which means that I need to put parentheses around that quantity if I ever break it apart. So now that that negative can be distributed to both terms, and we should recognize that log base 7 of 7 to the 1/2 is simply 1/2. So our final result is 1/2 minus this first logarithm minus the second logarithm. So let's take a look at another example where we are condensing multiple logarithms into one. So the first thing to recognize here is that 5 is not a logarithm. So I need to rewrite this as log base 3 of something so that I can combine it with the other log base 3 terms. Well, if 5 was the result of simplifying a logarithm, then that must mean that if the base of this logarithm is 3, then I need the argument to also have a base of 3. Now I just need the exponent to be 5, which is why it's log base 3 of 3 to the 5th. Minus the rest, or rather minus log base 3 of A plus log base 3 of B. Now it may be tempting to just combine these last two by thinking that, well, I see a plus sign between logarithms, and therefore I should be able to just use the product rule. The problem is that this logarithm has a negative out in front. So I can't actually apply the property of the product property because this isn't a positive logarithm plus another logarithm. So instead, we should simplify left to right. So let's start off by dividing the two arguments, since I'm subtracting these logarithms, which would give me log base 3 of 243 divided by A. And we drop down the next logarithm. Now that we have a logarithm plus another logarithm, this is where we can merge them by multiplying the arguments. And if we multiply 243 over A times B, we can simply put the B in the numerator, and therefore my final result is this single logarithm. So again, anytime we are expanding a logarithm, we're breaking it up into multiple terms. But by condensing a logarithm or an expression with logarithms, we're combining it into a single logarithm. Now there's one last property that allows us to take care of powers of exponentials. And this relates to the property of exponents that says if you ever have an exponential expression raised to another exponent, then that means that I can simply multiply the two exponents. So the property that shows this expression is simply if you have a logarithm with an argument involving an exponent. So notice n is the exponent. Notice that the argument is not a product. It's not a quotient. So I'm not going to use the product or quotient properties. But this one here shows that there is an exponent of n. So therefore, this property demonstrates that if we ever see an exponent inside of a logarithm, we can move that exponent to become the coefficient of the entire logarithm. So before, again, doing any examples, let's take a look at this proof. As we did before, remember that logarithms are exponents. So if I see an exponent of x up above b here, why don't we rewrite that as a logarithm? We'll just call it log base b of m. Well, by converting this into exponential form, that gives us b to the power of x is equal to m. Which now means that I can use this property to say if I have the power of m to the power of n, then I should be able to rewrite this as b to the x to the power of n, since m is the same as b to the x. But notice that by the property of exponents, I can rewrite b to the x to the power of n by just multiplying the two exponents. And therefore, I've got an expression that says m to the power of n equals b to the x times n. Now let's rewrite this as a logarithm, since I see that the base here is b. If the base is b, I could say log base b of the other side is equal to x times n, because x times n is the exponent. But notice we also know what x is. X, from the beginning of the problem, was log base b of m. So I can rewrite this property of logarithms as log base b of m to the power of n is the same as n times the value of x, which was log base b of m. So this is actually a pretty simple property to use and a pretty powerful property to use because this allows us to say that if I want to condense an expression and I see coefficients in front of a logarithm, that each of those coefficients can become the power of the argument. So this coefficient of 3 will become a power of 3. This coefficient of 1/2 becomes a power of 1/2. And this coefficient of 2 becomes a power of 2. And so now we recognize that there are no more coefficients. So because of that, we can now start simplifying by merging them using the product and quotient properties. Now, anytime we see fractional exponents, just keep in mind that that becomes a radical. So I could actually rewrite that as the square root of b. And now if I drop down the other two terms, I'm ready to apply the product and quotient rules. So let's just move left to right. Here I have a logarithm plus another logarithm, which means I can combine them by multiplying the arguments. But if we drop down that next logarithm, we see that now we have a logarithm minus another logarithm, which allows us to divide the arguments. And therefore, this is my final single logarithm that is equivalent to the original expression. Let's do an example where we're trying to expand a single logarithm into multiple terms. Well, the first thing I should recognize is that this argument is a fraction. So I could simplify that by simply breaking this apart using the quotient property. Take log base 4 of the top minus log base 4 of the bottom. Well, now I should recognize a couple of products here. For the first logarithm, I see 9 times the cubed root of x, which can actually be broken apart into a sum of 2 logarithms, minus, but now I should recognize the log base 4 of x squared minus 1 can be rewritten by factoring the argument. The argument is x plus 1 times x minus 1. So I can now recognize that this last logarithm is another product, and this first set of logarithms I can simplify by rewriting them as powers. So I could rewrite 9 as 3 to the power of 2, and I write cubed root of x as x to the power of 1/3. While we're at it, this second logarithm is a product, so I can break that apart again into the log of the first plus log base 4 of the second. But again, there's an issue. Since I'm subtracting the entire second logarithm here, then that means that I need to subtract the entire quantity, which needs to go in parentheses if I ever use the product rule after a subtraction. So now I can distribute the negative. I can also bring each of these two exponents to the front to become coefficients, and therefore this simply becomes 2 times log base 4 of 3 plus 1/3 times log base 4 of x minus log base 4 of x plus 1, and distributing the negative makes this last term minus log base 4 of x minus 1. So aside from the basic properties that allow us to simplify numbers, we also have 3 other properties, the product rule, the quotient rule, and the power rule, that allows us to break apart and combine logarithms if the argument is ever a product, quotient, or power. Now there's one formula that is going to also allow us to evaluate logarithms that are not like the powers that or the properties that we were dealing with before. Now most calculators, when you see them, will have 2 buttons. There will be a button that says log for log, and a button that says ln for the natural logarithm. So notice that the 2 buttons allow us to simplify logarithms that have a base of 10 or that have a base of e. The problem is, what if I want to use a calculator to find something like log base 2 of 6? If these are the only 2 buttons available to us, I need to somehow change the base to 10 or e so that I can use my calculator. So if I take a look at what we call the change of base formula, this formula will allow us to change the base of any logarithm notice log base b of a, to any base we choose. We'll call that base c, but we would typically like that base to be either 10 or e, simply so I can use my calculator. So notice that I could rewrite log base b of a as log base c of the top divided by log base c of the bottom. So notice, in other words, this is not the quotient rule. Notice that we're not dividing the arguments. What we're doing is dividing two completely different logarithms. So the proof for this is basically the same, where if I allow x to equal log base b of a, I can say that b to the power of x is equal to a. But notice that right now the base is b. What if I would like it to be a different base, like log base 10? Well, what I can do is I could take the log base c of both sides, which is allowed in algebra because I'm keeping this equation equivalent. If I now use the power property to bring the exponent of x to become the coefficient of this logarithm, I now get that x times log base c of b is equal to log base c of a. So if I want to solve for x, which is the same thing as log base b of a, then I can divide both sides by that quantity of log base c of b, which is where I get this quantity. That x is not only log base b of a, but x is also this quotient. And therefore, here's our change of base formula. Okay. So now let's take a look at an example of how we can use this in order to calculate or simplify to get a decimal approximation. So let's say we want to find a decimal approximation for log base 3 of 21. In other words, this is saying 3 to what power is going to give me 21? Well, we know 3 to the power of 2 equals 9. And we know that 3 to the power of 3 is 27. So since 21 is somewhere between 9 and 27, I know that the exponent will be somewhere between 2 and 3. But that's not good enough for us. We know that this answer should be 2 point something, but what is it? Well, log base 3 of 21 has a base of 3, and oftentimes in a calculator, we don't have a button that will allow us to calculate a base of 3. So instead, we're going to use the change of base formula to change this base to something other than 3. So we take log base c of the argument over log base c of the base. So just remember the base goes on the bottom. Now we could choose 10 or e because those buttons are in our calculator. So I'm just choosing it to be log 21 over log 3. And now if you punch each of those separately into your calculator, we get a couple of different decimal values. We now divide these decimals, and therefore our final result is 2.771, which is something we would expect because it's somewhere between 2 and 3. And we know that 21 is closer to 27 than it is to 9. So my exponent should be closer to 3 than it was to 2. Now I'd like you to see that because this change of base formula allows us to change to any base, what if we were to use our other button, our other logarithm, the natural logarithm? So if we change to a base of e, we would write it as ln of 21 divided by ln of 3. Notice if I calculate each of those separately, we get a couple of very different decimals than we did for the first one. But if I take their quotient, the value still remains the same. So notice that all of these properties are what are allowing us to take an expression involving logarithms and change it into a different form. Oftentimes, expanding a logarithm into multiple forms makes the problem easier for us, while a lot of times taking multiple logarithms and combining them into one will also make the problem easier for us as well.